So, what exactly is a coordination compound? Well, basically, we're talking about a compound that involves bonding interactions between a metal center. So, this metal can be an atom. And when I say that it's an atom, what I mean by that is that it's in a neutral form, or it can be something that is an ion, okay? And that means it's charged. Typically, we're talking about something that's going to be positively charged. And so, in the field of coordination chemistry, we're looking typically at transition metals. And so we're seeing the interaction between these transition metals with one or more things that are called ligands. Now, in terms of the very basic chemistry that we're focusing on, we're looking at this type of bonding interaction where you have a metal, here defined by the generic label M, interacting with a ligand, here defined by the generic label L. And so what we're focusing on principally is a pair of electrons that has the capacity to form a bond with a metal center. So essentially, those electron pairs are going to be drawn to the metal, and what you're going to form is a metal ligand adduct. All right, so that's a very simple type of explanation of what is at the root of a coordination compound. But let's look more deeply in terms of some of the fundamentals about what is drawing this metal and this ligand to interact. So this goes back into the principles of Lewis acid base chemistry. And so what we're basically looking at here is the metal playing the role of a Lewis acid and the ligand playing the role of a Lewis base. Okay, so we're going to define that in a moment if you guys don't remember what that is. And so we're looking at that Lewis acid and that Lewis base coming together, forming this metal ligand bond. All right, so let's review then what is the Lewis acid base theory. All right, so essentially here, we're defining an acid as being something that can accept a pair of electrons, where a base is something that can donate a pair of electrons. So in that context then, that explains why in that reaction that I just showed you, the metals are the Lewis acids because they're actually accepting the electron pairs that are being donated by the ligands. So in terms of classifying ligands then, they can be atoms, ions, or molecules. Okay, so that means they can be neutral or charged. And so they're donating their electrons to the metal center. So here we're looking at a very simple metal compound, one that's being formed between silver with a charge of +1 or oxidation state of 1, interacting with two molecules of ammonia. So in this context then, remember, the silver is going to be your Lewis acid, your ammonia molecule is your Lewis base, and here we're focusing on the nitrogen center of that molecule because it has a pair of electrons that are capable of interacting with the silver, of forming an adduct. And so we have two of these molecules, and so essentially you're looking at that pair of electrons being drawn to the silver, all right? So essentially then, with the equivalency that we have there, we form this linear compound where you have the silver center interacting with the two ammonia molecules forming two different bonds. Now, let's explain the context of these bonds. And so traditionally when we were taught about bonding or bonding interactions between two different species, we were taught that we're having a sharing of electrons coming from the two members that are forming the bond. Okay. In this context, we're still having a sharing of electrons, but the electrons are coming exclusively in this particular context from the ligands. And so here we're focusing on a type of bond that is called dative. So the electron pair is coming from the Lewis base. So this type of bonding interaction is what is referred to as a coordinate covalent interaction. All right, so let's break that down into what does that really mean. What that means is that when we're focusing on these metal compounds, these metal bonds interactions, we're looking at something that features both covalency, so as we're familiar with, a sharing of electrons, and ionicity, right? So that idea of a distribution of charge where something is cationic and something is anionic. So you have a mixture of these features. All right, so let's try to define some of those ligands, as I already stated, that they can be neutral or they can be charged. And so here I'm just giving you a representation of some more, I would say, well-known ligands. Right? Obviously, ligands can be a large set of molecules that can interact with a metal center. All right, so here we're focusing on a subset, those that are neutral. And so, as an example, you have the amine ligands, right? So, amines have those nitrogen centers with a pair of electrons. So, they're not drawn there, but you can imagine that they're there. They're accessible to interact with the metal center. All right. Other types of ligands that are also neutral can be water. And so, something that is very important is to recognize that solvent molecules can play the role of ligands. And when we're talking about a metal in the context of a solvated environment, the metal won't actually exist as a free entity. It can exist as a compound with the solvent. So, you have these other molecules that also play the role of a neutral ligand. So over here, what we're looking at is a subset of ligands that have a charge. And so they are anionic, right? So negative charge. So you have the halides, okay? And so these are the common names that are attributed to these particular ligands when they coordinate to a metal center. So for instance, fluoride, when it coordinates to a metal center, will be referred to as a fluoroligand. Chloride will be referred to as chloro, and so forth. Then you have those type of anionic ligands that are referred to as pseudohalides. So they have that -1 charge, and you see the associated common names to refer to these particular ligands, right? And so this just gives you an overview of these sort of small molecule representation of anionic species. All right. So it's not so common, but there are examples of ligands that can be cationic. And here I'm giving you just a subset. There are not really that many. So we have this particular nitrogen-based set of ligands. So hydrozinium and also the nitrosyl ligands. And so they're positively charged. And the reason why they're not so common is if you think back to this idea of the interaction between the metal center, metals are often positively charged. So imagine having a positively charged ligand, right, interacting with a positively charged metal, right? So that positive interaction can cause from some amount of electrostatic repulsion. And so there are going to have to be some other factors to counter that repulsion in order for you to have a thermodynamically favorable, right, a thermodynamically favorable adduct between the two of these. And so those are things that you have to think about is, what's really drawing a metal ligand to interact, right? And so the electrostatics can be a factor. All right, so another important property to generally characterize ligands is in terms of this property known as denticity. And so if you look at the root of that particular word, dent, referring to dental, right, this idea of biting onto a metal center. So essentially what this particular term defines is the number of atoms at which a ligand can bind a metal. And so let's consider an example in order for us to be able to explore this. So here we're looking at water, and water is referred to as aqua ligand, right? And so when you look at the oxygen, the central atom here, well, we know that oxygen has two free pair of electrons, right? So it has the capability of forming a dative bond with a metal center. We have these two free pair of electrons. And so let's imagine that we do form a compound or a bond with a metal. And so here, what we see is that the oxygen is forming one bond to the metal center. So we have a way to classify that interaction between the water molecule and the metal, and it's based on its denticity. So here I just want to give a little bit of an indicator of how you can generally predict where you're going to see the interaction. So here, coordination typically can occur at the most electronegative atom. That's not always the case. But when we're generally starting to characterize coordination compounds, that's where we should draw our attention to. All right, so we know oxygen in the water molecule is the most electronegative metal. All right, so then what we do is we use prefixes to distinguish the denticity of the ligands. So here we know we have a 1-point contact between the oxygen and the metal. So here then, the coordination demonstrated is a coordination that is referred to as monodentate. Again, because of the metal binding at one atom in site. So I will, just to let you know, guys, if you do have any questions, feel free to ask me so that I can stop to explain anything a little bit more in depth. All right, so then referring to this idea of prefixes to define the denticity. So here's just the representation of the prefix and then the number of coordinating atoms from a given ligand. So if you have one coordinating atom of a given ligand, as we just saw, that will refer to something as being monodentate. If you have something that has two atoms, well, that would be bidentate. Three atoms, tridentate. And so you see the trend there. Okay, something that's very important in terms of classification is that how many atoms are actually coordinating to the metal center. So we're going to look at here just as an example of a metal compound. So here, what I've depicted is a metal that's coordinated to these generic ligands, X, okay? And so if you're not familiar with this drawing and what it's representing, it's trying to depict a three-dimensional representation of structure. And so in a moment, I will go a little bit more in depth about what I mean about structure. But here we have a coordination number of 6, okay? And what do I mean by coordination number of 6? Well, we have 6 contacts to the metal center, okay? And so typically when we have that type of contacts, a coordination number of 6, we have this geometry, which we refer to as octahedral. And I will go into more depth in terms of defining this. But one thing is very important is try to see these things in terms of a three-dimensional perspective. This is not a drawing that's meant to be looked at as a two-dimensional drawing. And what I mean by that is that we're supposed to be looking at this, where you have these two ligands that I've drawn here that are right on the plane of your screen, okay? But then when I draw these wedges, if you guys have seen in organic chemistry, okay, these wedges indicate perspective. And so they're meant to define that we're looking at this at a plane that's perpendicular to your screen. So when I have these wedges like this, what I'm trying to indicate to you is that these are bonds that are moving behind the plane of your screen. And then when I have these wedges like this, what I'm trying to indicate is that we have a bond here that's coming towards you from the perspective of your screen. So that's just to give us a three-dimensional perspective of how these points of contact are occurring. All right, so with regards to denticity then, if we have an atom, or in this case, let's say a molecule, but we're just representing it by the letter A, and it has only one contact, okay, just as we mentioned already, well then that will be referred to as something that is monodentate. But then let's imagine that we have a molecule that has two contacts. Again, as I already have shown you the list, but I want to give you a visual of this. Well, then this has these two contacts, right? And you see that there's a bridge that you have a ring that can form, right, because of these two contacts from that ligand. Well, that is something that is bidentate. Then you have something that is tridentate, okay, and you see the associated rings that are forming, okay. Then you have something that is tetradentate, and then you have an example of something that's pentadentate, and then you have something as an example as something that's hexadentate. All right, so this is really important. And so I will note to you that just because a ligand can have the capability of being, let's say, hexadentate, like for instance, as we can see in this example, doesn't mean that in every case it will bind a metal at all 6 points, right? There could be a number of factors, steric factors, that can prevent a ligand from reaching its full denticity capability. All right, so a really important distinction to make in terms of terminology. So a ligand that can bind at 2 or more sites is referred to as something that's being polydentate. So that's just the general term. But more commonly, we know this as being something that is a chelator, right? And so you probably have heard the term, if you've taken inorganic chemistry, but you probably have heard the expression of chelation therapy. And that's pretty common when a metal is trying to be stripped from the body, if it is in excess and causing some sort of toxicity. All right, so a related concept to denticity is the concept of hapticity. All right, so here we're looking at that this idea of how the electron density within the particular ligand is interacting with the metal. So it may not necessarily be points of contact directly with atoms, but with electrons that are available to bond to a metal center. All right, so this is expanding this concept of how we can define a metal complex. So the coordination of a ligand to a metal center via an uninterrupted and contiguous series of atoms defines what is hapticity. And so we use a symbol, and this symbol is eta, to represent this idea of hapticity in terms of how many atoms are participating in this interaction. All right, so let's give an example of this. So let's consider this particular molecule. What we have here is a representation of cyclopentadiene anion, okay, so cyclopentadiene anion, which is drawn here. And this molecule, in fact, is not actually very stable. It often, if you try to have it in its monomeric form, it will form into a dimeric form. But we're going to focus on it in terms of it being in this monomeric form, in this anion. And we're looking at the electron density, or the electrons that are available to interact with metals. All right, so we have, as you know, this free pair of electrons there. But also what's available are these additional bonds, these double bonds, that have the capability to interact with the metal center. So this is really important, because then that expands this concept of what are electron pairs that have the capacity to bond to a metal. So these are 3 electron pairs, right? So one that is free, 2 that are bonded. So in this case, 2 double bonds, right? And so those have the capability of interacting with a metal center. And you're going to see how that can then lead to a different number of atoms from this molecule interact with the metal. So if you look at this ring, there are 5 carbons that are available here, right? So that's something for us to consider. All right, so let's look at this representation to distinguish between the hapticity of this particular molecule interacting with the metal center. And it is something that is anionic in terms of its interaction with the metal. So what do we see here? Well, we see different representations of how it can interact with that metal. So over here, we have a 1 atom interaction with that metal. And so what we can think about when we look back in terms of the molecule that we had previously, that was, as we were showing it in a form that was not chelated. So let me just clear this, right? So where is that point of contact going to be? Well, likely that point of contact would be where there is that free pair of electrons. Okay, so we see that there. But now let's focus on the other 2 representations. Well, we have this metal that's interacting with a contiguous series of carbons, and so we see the interaction with 3 carbons there. And then we have this representation where it looks like that metal is interacting basically at the center of that molecule. So it's basically interacting with all of those 5 carbons. But the way we really need to think about it is in terms of the electrons that are really contributing to that interaction. All right, so then how do we represent the hapticity of these interactions? Well, we have the first one, which is eta 1. That's the 1 point of contact. The second one, which is eta 3. Okay, and so let me just clear up those markings that I have there, so you can see that I have some stars to represent the atoms from the ligand that are interacting with the metal center, and then you have eta 5. Okay, so they have all 5 of those carbons that are participating in the set of electron pairs interacting with that metal center. Now, one thing to note is that they are related, but they're not identical, hapticity and denticity. Okay, so they don't always go hand in hand, because there's a little bit of discrepancy in the literature in terms of how hapticity can relate to coordination number. All right, so let's explore this. What do I mean by that? That can be a little bit confusing. Well, let's look at this. But for instance, eta 5, and so we have the representation of eta 5 right here. So by some, eta 5 may actually be considered as a coordination number 5. Well, why coordination number 5? Well, you are in fact interacting with a 5-carbon ring, right? So those 5 carbons are participating in this feature. Others might see this as a coordination number 3. Well, why coordination number 3? Well, that's because you have 3 electron pairs that are contributing to the bonding interactions. Remember, what's underlying the bonding interaction is the availability of electrons being able to be shared, right? We have these coordinate covalent interactions. All right, so there's a bit of how do you really describe this coordination? Well, let's look at this in terms of this particular molecule. How do we classify the coordination number of this molecule, titanosine dichloride? Well, we have the ligand here, and it's coordinated to the titanium. So someone who is brave, what type of hapticity is represented here? You can get on your microphone, you can type
5.
into the chat. So Claudia says 5, 8 of 5, right? And that's correct. Both of these have an 8 of 5 type of interaction with that titanium center, right? And so that would imply that you have the 5 carbon ring interacting, so those 3 pairs of electrons interacting with the titanium. And then you have the chlorides that are interacting with titanium, and that's more of the traditional thinking of the monodentate interaction of the chloro groups with the titanium. All right, but then how do we describe those in terms of a coordination number? Well, is this a coordination number 8 or even a coordination number 12? Well, where are we getting these numbers from? Well, if we were referring to a coordination number 8, well, that's because we're thinking about this as terms of 3 electron pairs, right? 3 electron pairs per each ring. And then you have the set of the 1 electron pair from the chloro groups that are interacting with the metal center. So then you would have a total of 8 electron pairs. So that's where that potential coordination number is coming from. But what about the possibility coordination number of 12? Well, 12 will be coming from the fact that we have 5 carbons here, 5 carbons here, and then you have these 2 chloro groups that are interacting with that metal center. So then that then would suggest that this is a coordination number 12. But then there's another thing that can make this confusing, is that, well, there's also this correlation. So anyone who's taken inorganic chemistry between the geometry and coordination number, where if you look at this compound in terms of its geometry, this is a tetrahedral geometry. Okay, so you guys are all familiar with tetrahedral geometry as you've taken organic chemistry. And so tetrahedral geometry implies a coordination number of 4. So here it's quite complex in terms of thinking about this idea of what is the actual coordination number that's really represented here. And I would say that it's not always very clear. But let's use that as a segue to then explore this idea of traditionally how coordination number lines up with geometry. And I will say that this is more in terms of an ideal representation. Real compounds, especially in a biological context, are not this idealized. All right, so let's focus on this for a moment, though. So coordination compounds adopt highly organized structures. That is absolutely true, no matter what. We'll see in terms of how they can crystallize, you will see these organized structures. And depending on the nature of the ligand, they can then induce a predictable geometry. So coordination number, abbreviated as CN, can dictate an idealized geometry. So let's explore this idea. All right, so coordination number 1, that's very overly simple. That's obviously a no-brainer. Here we have a representation, but linear, but that's basically, 2 atoms forming an interaction. This is 1 bond. But really, this idea starts when you start with coordination number 2, where typical coordination number 2 would dictate a linear geometry, as we saw when I was talking to you guys about silver plus interacting with the 2 ammonia molecules. And so, in terms of a generic representation, what you have is this interaction of the 2 ligands with the metal center. And so what you have then is a ligand-metal ligand bond of 180 degrees, right? So again, idealized representation, assuming that the 2 ligands are identical. All right. But then you have coordination number 3, which represents a trigonal geometry. So let's look at that representation. And so here we have a drawing to look at this trigonal geometry. And so we have a defined bond angle, ligand-metal bond angle. And so throughout, each one of these will be 120 degrees. Right? So again, visualizing this in terms of it being a planar structure on the plane of your screen. All right, let's go further. Now let's go to something, a coordination number 4. Now here it gets a little bit more complex, where you have 2 possibilities. One of the possibilities is tetrahedral, as we already mentioned, right? So a drawing that is tetrahedral, let's have a representation of this. Now again, I will call your attention that do not look at this drawing as something that is flat. It is not flat. The way that we are using the wedges implies that those particular ligands are located in a plane that will be perpendicular to the plane of your screen, of your laptop screen or your telephone screen, however you're looking at this presentation. All right, so these two ligands over here, they are in fact on the plane of your screen. But these two over here, those are actually in a plane perpendicular to your screen. All right, so tetrahedral, you guys are all familiar with this. So there's going to be then an associated bond angle, ligand metal bond angle that you guys are familiar with, and that is of 109.5 degrees. Okay, so that's the classical representation of tetrahedral. But then let's look at another possibility where a coordination number 4 can actually lead to a square planar geometry. And so then what's the difference? What does square planar mean? Well, as the name implies, it is going to be a planar structure. So let's look at that structure. And so here we have that structure represented, where we have all those ligands bonded to the metal on the plane of your screen. Okay, and another really important thing is that you have a distinct ligand bond angle, where you have everything at a bond angle, and from this context of 90 degrees. So this is 90 degrees, this is 90 degrees, this is 90 degrees. Okay, so that helps us to then distinguish between these two different geometries for coordination number 4. All right, well, what about coordination number 5? Well, then you can also have two different geometries. One is trigonobipyramidal, and let's have a representation of what is trigonobipyramidal. Okay, again, we need to look at this as something that is three-dimensional, where we have two different positions for how the ligands are interacting with the metal center. So here we have one position that is referred to as the axial position. So that those two ligands are on the plane of your screen, and the ligand-metal ligand bond angle is 180 degrees, so a straight line down the plane of your screen. But then you have the other three ligands that are on a plane, okay? And then two of these bonding interactions, they are perpendicular to your screen. So they are on a plane perpendicular to your screen, okay? And so now there's going to be another distinguishing features where you're now going to have different ligand-metal ligand bond angles. So let me clean this up so you guys can see this better. All right, so let's distinguish these ligand-metal ligand bond angles. When you're focusing on a ligand from the axial position interacting with your metal, and then from the context of a ligand that is in the equatorial plane, well, that ligand-metal ligand bond angle is 90 degrees, okay? But if we're focusing on, in this case, a ligand that's in the equatorial plane, bonded to the metal, and then interacting with another ligand in the equatorial plane, well, that bond angle is 120 degrees, right? So that we have these two distinguishing bond angles representing a trigonobipyramidal structure. All right, well, what is the other option for coordination number 5? Well, that would be square pyramidal. All right, so let's look at what square pyramidal is. Well, then here, square pyramidal looks like this, where we have 4 ligands in a certain position, and identical positions with respect to the metal center, and one ligand that is in a distinct position. So we have 2 different positions here, similar to trigonobipyramidal. We have then the axial position, and then we have an equatorial plane. And so now we're going to distinguish between these two geometries in terms of the metal ligand, so the ligand-metal ligand bond angles, where here, all the ones that we see are 90 degrees, okay? And so then where is that square pyramidal name coming from? Okay, so when you see those names, it has to do with the way you can draw the connections between the ligands. So you have that square component, right? And then if you draw from the ligands down, you get that square pyramidal structure. Very similar to what you see for the trigonobipyramidal, right? You have this trigonal structure, right? And then if you draw and connect the ligands in the equatorial plane to the apex, so one of the ligands in the axial position, you have one pyramid there, then you have another one here, and then, of course, I'm having difficulty there drawing that, but anyways, there it goes. Okay, so you have those 2 pyramids, and that's why it's bipyramidal there. All right, let's advance then. Let's go to then coordination number 6. All right, so this particular coordination number and this particular geometry is commonly used to explain a number of different properties of coordination compounds. So the ideal geometry is octahedral. And again, I'm going to emphasize ideal, meaning that all the ligands are identical, and then you don't have steric restrictions that can result in a deviation from this geometry. There are a number of factors that can actually result in distortions. All right, but focusing on then this particular geometry, here too, we have two different positionings. But I will tell you that even though formally there are two different positionings, they are in fact, there is no difference between any of the ways these ligands are positioned on this metal. The reason for that is that you can rotate this molecule in any fashion and you will see that every ligand position is actually identical. So formally, there is a distinction, but in reality, there isn't when you're talking about a metal ligand compound in which all of the atoms that are connected to the metal are identical. But again, using this formality, you have the axial position, and then you have the equatorial plane that is perpendicular to your perspective, and perpendicular to the plane of your screen. And then you have the corresponding 90-degree bond ops, ligand bond angles. Okay. Any question before we move on? This idea of correlating coordination number and geometry. Again, you can post your questions in the chat. All right. So now that we have a sense of structure, because I think that's really important, just to be able to visualize things. And so that's often when I read a paper with metal compounds, I try to visualize what are these compounds, what do they look like? And for me, that's very helpful, especially when we're talking about functionalities of these compounds and this idea of the compound undergoing change. I like to visualize that change that is actually undergoing structurally. All right, so but let's focus a bit on what's drawing this metal ligand interaction. So we did mention electrostatics, but let's dive a little bit more into the Lewis acid-base theory. And there's a component of this theory that's referred to as the hard-soft acid-base theory, or the HSAB theory. And this really underlies the preference for metal ligand interactions. It actually underlies the preference of many species interacting with one another. All right, so again, this is an extension of the Lewis acid-base concept. This was originated by Pearson and Chat in terms of recognizing the polarizability of species. Okay, this polarizability of species. Now, what does that mean? This idea of the movement of electron density within a species, right? And how fluctual that is, or how stable or localized it can be. Well, that polarizability of species was correlated with the preference of one species to interact with other species. All right. Well, let's try to look at this in terms of a specific example. Okay. So here, let's imagine, since we are using the acid-base concept, then let's consider a random base. Okay, that's interacting with a non-polarizable Lewis acid and a polarizable Lewis acid. So what does that mean? A Lewis acid where you have a localized electron density, and a Lewis acid in which you have more fluctuating electron density. All right, so here is a representation. The proton as something that is a non-polarizable Lewis acid interacting with a generic base, which we represent here B, in terms of it having a pair of electrons. It is a Lewis base, right? It can donate electron pairs. Okay, so we're focusing on then the thermodynamics of this, the equilibrium expression. So K as a representation of strength of bonding. Okay, we're forming these protonated adducts, these HB adducts, versus a polarizable Lewis acid. All right, so polarizable. Well, it turns out we're looking at here at this methyl mercury species, where the mercury is something that is quite polarizable. Okay, so that interacting with a Lewis base, we're looking at the strength of that interaction, okay, forming this adduct, this mercury base adduct. All right, so then from this perspective, what we're looking at then is what are known as affinity scales, the strength, the relative strength of different bases with the non-polarizable Lewis acid and the relative strength of bonding to the polarizable Lewis acid. Okay, so here I'm just redrawing these interactions. Now we're going to have some formal definitions. Well, it turns out that if the affinity of that base, a given base, is higher for the proton much higher for the proton than it is for the methylmercury, well, that base is referred to as hard. Okay, so that is, it is non-polarizable, and a really important feature, has a high charge to size ratio. Okay, that also implies that the proton is something that is a hard species as well, but we'll see that in a moment. Now, if the affinity for the proton is much, much weaker than the affinity to the methylmercury, well, that defines the base as being something that is soft, meaning that it's polarizable and it has a low charge to size ratio. So as you can imagine, you're going to have your in between. Okay, so something that has approximately similar affinity to both the proton and to the methylmercury, to the non-polarizable Lewis acid, the polarizable Lewis acid. In that case, then the base is intermediate or borderline. All right. But how do we readily identify something as hard or soft acid base? Well, let's look at a periodic table, okay, and that's going to be really important. And we can have to recall some periodic trends that you guys were taught in general chemistry. These will hold true in helping you really get through some of the basic understandings of what defines these types of species. All right, so in one of the major periodic trends that you discussed was the periodic trend of size, right? And so when we look at a periodic table, when we're going down a particular column, you see that the size of the elements increases, right? So we go from small to larger. Then when we're going from the along the row, right, along the primary quantum number, depending on which row you're in, well, you see that the elements typically will decrease in size. Okay, so that's something really important to keep in mind to give us a perspective. And why is that? Because the hard-soft characterization, or even intermediate, will depend on the charge to size ratio. That's going to be a critical component here, right? So that the lower the size and the larger the charge is, the greater the hardness of that species. And something that's going to be related to this is the electron negativity, right? That idea of an element holding on to its electron density, right? So that goes into this idea of polarizability. So the electronegativity of elements can be really important here, whereas the larger the electronegativity, which means that you're going to have a larger localization or holding on to the electrons and a larger hardness. Okay, that gives us a perspective. But also, we can have a perspective of where you would expect to see hard acids in terms of the periodic table. All right, so here I'm giving you a list. Hard acids would be alkaline metals, alkaline earth metals, and then in the alkaline metals, you also can include proton. It is a hard acid. And there are some studies that suggest that protons can have metallic-like properties. Another area is in the transition metal area, the first row, that when those metals are of a high oxidation state. All right, so if we go back over here, we're talking about here. Okay, we're talking about here. And then we're also talking about the first row of the transition metals. All right, so those are the ones that we'll typically see as being hard, transition metals that are of a high oxidation state. Well, what about soft acids? Well, typically the second row or lower of the transition metals in low oxidation state. Right, so then that means that when we look over here, well, you can also have, to some extent, soft acids here, depending on the oxidation state, but we're typically focusing on things that are in this region, in the second, third, and so forth, in terms of you're getting things that are becoming softer. All right, here I'm presenting you this periodic table that helps to give us a little bit of more perspective. And so you guys are familiar with this. You guys are familiar with what makes something a metal and what makes something a non-metal, okay? So that would then easily help us to distinguish between things that are a Lewis acid and things that are a Lewis base, right? Something that is a metal will fall into the category of a Lewis acid, and something that is non-metal would fall into the category of something that would be a Lewis base. All right, so that's an English, sorry, that's an easy distinction there, right? So that you can see that there is a break here to help us to see that. But then we can then further characterize things in terms of their hardness, and you will see that it can be a little bit difficult. So as I was mentioning to you, you have these two columns, alkali earth metals, that are hard, but this hardness, as you go down the columns, will become less so. So as you reach the lower ends of these columns, they will be more in the intermediate region. Okay. When you look at the transition metal section here, well, you see that deviation from, as in the first row, that there are typically hard, borderline, and then as you move down the rows, you will start to see that they become softer. And you have some, like for instance, iron, that actually is that can be, depending on its oxidation state, something that is hard or something that is borderline. Okay. To the right over here, where we're focusing on those things that are, that can be non-metallic, right? So here, then we can look at how you go from very few examples of things that are hard to then very quickly see that there are things that are going to be quite soft. All right, and so that can give us a perspective of the chemistry that are possible. And so you have then the categorizations of the hard, borderline, and soft acids and bases, just to give us a perspective of all these things. All right. Again, any questions, please post them up. All right, so I keep emphasizing this idea that hard, intermediate, and softness, but particularly hard and soft, those extremes, those are relative terms, okay? So we can see how that can be really dictated by the nature, especially as we explore a metal compound, that can be dictated by the nature of the ligand, and also can be dictated by the nature of the metal and its oxidation states. All right, so focusing on the ligand. Well, something that can really alter or fine-tune the relative hardness of a ligand is if you see resonance present. So resonance can actually decrease the relative hardness of a ligand. So let's look at this example here. So we're focusing on this carboxylate type molecule here. And so here we see that a resonance can exist, where you have this double bond that is resonating within this particular two sets of oxygens. So you see the double bond here and then the double bond over here. Okay? So you have this equilibrium between these two structures. So formally, if you look back at that periodic table, let's go back. Formally, when we look at oxygen is something that is a hard base, right? But then in a particular structure like this, well, then the oxygen will be less hard because of that resonance, okay? Relatively less hard. That doesn't mean that it drops so much, but it is relatively less hard, especially if you compare it to this type of a molecule, this alcohol, okay? This alcohol that's in its anionic form, so that will be ethanolate, okay? Where those electrons are localized on the oxygen. Another contributing factor, although I'm not going to emphasize too much, is those other things that are connected to the oxygen and how they can play a role in terms of fine-tuning the relative localization of electron density. Okay, so here you have a localized electron density in the alcohol. A very interesting thing, I'm going to clean up the markings there, is that now carboxylates actually have the capacity of being both monodentate, okay, so coordinating a metal from either one of those oxygens, but also really importantly, can play the role of a bidentate chelator, and actually a really important one. So there, that capacity of denticity can also play a role in terms of the relative hardness as well. Okay, now let's look at the contribution of transition metals here. Well, for transition metals, the relative hardness will be dictated by the oxidation states, where we focus on iron. A difference of one oxidation state is enough to really transform iron from being hard, so when we look at it as in oxidation state of 3, to then being something that is intermediate for iron 2. So that one oxidation state difference is enough. So how do we see this in a better context? Well, let's look at an example of the potential ionic radii that iron 3 and iron 2 can adopt when they are interacting with a ligand. And we have to be pretty specific, so we have to make this comparison pretty tight. So imagine a metal center that can form a coordination number 6, okay, so 6 coordinate radius, while iron 3 has a radius of 69 picometers, whereas iron 2 has a radius of 75 picometers. So that tells you there, the difference in size, which can be very important. All right, so now that we have this perspective of hard, intermediate, soft, and even that there can be a gradient of this depending on where a particular atom is located in a molecule, or in the context of a metal, its oxidation state. Well, let's talk a bit about this idea of the principles of hard, soft, acid-base interactions, this idea of binding preferences. Well, it turns out that hard acids prefer binding to hard bases. Very similarly, we have intermediate bases prefer intermediate bases. Intermediate acids prefer intermediate bases, and soft acids prefer soft bases. All right. So that's something that can, if you can identify a given hard, soft property of a particular species, then you can start to predict types of interactions that may occur. Okay. These interactions are stronger than those between mixed species, so stronger than between hard and soft species. That doesn't mean that a hard and soft interaction can occur. It's just not something that will be preferred. Not a strong thermodynamic drive. All right, so let's use this theory to understand some of the common ways metals bind to biological species. All right, so we're going to just get a beginning insight into this. All right, so we're going to focus on then, in a very simple way, metal complexation by biological species. So let's first focus on metal interactions with proteins. All right, so you guys are, to some extent, familiar with proteins, especially if you're taking biochemistry. You have a perspective of the different stages of structures that proteins can actually adopt. All right, so when we're focusing on proteins, and proteins are polymers, they are polymers of amino acids. We essentially have to start from then the monomeric building blocks of the protein, and that would be the amino acids. So let's start from there. All right, so the metal binding atoms are typically located in the side group R. All right, so let's look at a generic amino acid. Here I have the drawing of a generic amino acid where you're focusing on the carbon, and you have 4 different groups around it. You have the side group R, which I'm just represented by that label R. You have a proton, and you have the carboxylic acid group and the amino group, okay? The way I have drawn it here is in its sort of ionic form. So you have the amino as positively charged and the carboxylate as negatively charged. Okay, this is a representation of the amino acid. All right, so I'm emphasizing that because I want to make sure that you guys are clear when I'm saying that the metal binding atoms can be located within the R group, but they also can be located within the amino group or the carboxylate oxygens. Okay, these have the capability of binding metals. And so if we look then at the collection of the 20 common amino acids, well, what we're going to focus on is that the metal binding atoms are typically located, and we're looking at where they're going to potentially form a bond to a metal. So here I have a few of them listed, not all 20 of them listed. And what I'm showing you here is the presence of the serine, which has an OH group here. So we were focusing on the R group. And if you look at the type of element that oxygen is, it's a base in terms of a Lewis acid definition, and it's a hard base, right? So you would expect a hard metal to be able to interact with the site. Where in contrast, if you focus on a cysteine, right, a sulfur, well, sulfur is actually something that's going to be a soft Lewis base. So then you have other types of amino acids like threonine, which has an OH group, methionine. And so again, we have the similar types of analysis that you can do, where you potentially might be able to find certain types of metals interacting with these. Here are another set of amino acids, okay, and where we will potentially find metal interactions. With tyrosine, that's a really common one, where metal can bind to the oxygen there. Histidine would combine to either one of those nitrogens. And in a histidine molecule, nitrogen is one of those that can be between intermediate and hard. Well, this is typically considered an intermediate site. And that's one of the reasons why histidine plays a really important role in biochemistry in terms of facilitating acid-base type catalysis. Okay. You also have lysines that can interact with metals through the amino group of the side group. You have the aspartic acid, glutamic acid, or typically you're talking about aspartate and glutamate interacting with metals. Okay, so here again we have the perspective of whether they are hard, intermediate, or soft, based on the atoms that have the capability of coordinating to a metal center. Another really important thing, and I alluded to this, is that you can also have more than one binding modality. Okay, so more than one binding mode. As an example, if you have a carboxylate, right? So we know that every individual amino acid has a carboxylate group, and then depending on the side group, if it's a glutamic acid or aspartic acid, they also have carboxylic acids. Well, the carboxylic acid can coordinate in a monodentate fashion. It can also coordinate in a bidentate fashion. That's something just to be aware of. Histidine, as I mentioned already, has the capability of binding a metal at either one of those nitrogens. Right. So here's just an example where it's binding to that delta nitrogen, and then over here is binding to the epsilon nitrogen. Okay. Now, it really depends, especially in a biological system. If you're talking about a protein and what other amino acids are available, how the steric hindrance can cause a metal to bind to one or the other. Okay, so it's not always so clear cut where it's actually going to bind. All right, so here are other examples of the metal coordinating to amino acids. So here's metal coordinating to the primary amine of the lysine, metal coordinating to the sulfur of the methionine, metal coordinating to the sulfur of a thiol group for cysteine, metal coordinating to the oxygen of tyrosine. All right, just to give us a perspective. All right, so now we talked about the amino acids, so that's the building block, that's the monomer of the proteins. And now we have to think about, well, the actual polymeric form. And so how do you get from the monomers to the polymer? Well, you have to invoke then the formation of what are known as amide bonds. So the amide bond then is the coupling of the carboxylic acid from one amino acid to the amino group of another amino acid, forming this amide bond here. All right, so then what happens when you have this, then what is essentially the amide backbone, is that you start to introduce additional binding sites. So here, here when we're looking at the perspective of the sequence, okay, we're looking at the sequence going from the N terminal, okay, and you will often come across this in literature, the N terminal, which means the first amino acid referring to its amino group, and then the C terminus, which refers to the last amino acid of the sequence and its carboxylic group. Okay, so N terminus, C terminus. Well, we see how those can serve as metal binding sites, and there are plenty of examples. We also have metal binding occurring at the backbone and also at the side groups of the amino acids. So these are introducing different sites that are possible points of contact with metals. So here I'm just drawing you the perspective of how the metal can interact with the amide group. So here is the amide bond, and that can exist in resonance, right? So that the double bond can be within between the carbon and the oxygen, also between the carbon and the nitrogen, and how that can induce a delocalization of charge, right? Well, it turns out that the metal can bind to both sides. So it can bind to the oxygen. I'm just drawing it here. I don't have it drawn on the actual slide, but I'm just drawing it here. Or an example, it can bind to the nitrogen of the amide bond. So those are capabilities, and there are plenty of examples of this. All right, so let's look at a particular protein, and we're going to focus on metallothionein, abbreviated here as MT. This is a really important protein. It has the capability of binding zinc, and zinc 2+ is an intermediate metal. So just to give us a perspective, hard, soft, acid-base chemistry here. Okay, so then you have to start thinking about, okay, what is something that's intermediate that might be able to interact with zinc? Well, a little bit of context. Metallothionein is the collective name for a large family of low molecular weight proteins that are present at very high concentrations. So 2 millimolar in the context of cells is extremely high, okay? Maybe from our perspective, 2 millimolar is not that high, but in the cellular environment, that's super high. Well, this particular protein consists of a single polypeptide chain, okay? So is one unit of 61 to 62 amino acids. One third of those amino acids are cysteine amino acids. So this particular protein has a very high cysteine content. Okay, so cysteine has a thiol side group. So this is a softer amino acid. Okay, and zinc is an intermediate. So you can imagine that there's going to be some interaction. It's not going to be I would say the most stable, right? If you're talking about one sulfur interacting with one zinc. But what's going to stabilize the interaction between this zinc and the cysteines? Well, what's going to stabilize is having a series of bonding interactions, right? So the more contacts, the more stabilized these will become. So it turns out that metallothionein plays a really important function as a storage of zinc and also plays a really important function as a storage of copper 1 and copper 2. And so if you look at the sequence, so these are the amino acids, right, represented from the N terminus to the C terminus. You'll see that you have a number of cysteines here. Remember, there are 20 cysteines here. And here's just a representation of the contacts between the zinc groups, the zinc metal centers. And so what happens is you have two types of metal binding domains, where you have the alpha domain. The alpha domain is depicted here, which consists of 11 cysteines interacting with 4 zinc ions. And then you have the beta domain here, where you have 9 cysteines interacting with 3 zinc. All right, so let's look at that. So you have the alpha domain, you have 1, 2, 3, 4 zincs, and then the beta domain, 1, 2, 3 zinc. All right. So that gives us a perspective. Another important thing is to look at the coordination geometry. So what type of coordination geometry do you see for the zinc on all these sites? Nathaniel, since you asked the question, I'm going to ask you, what is the coordination that you see for the zinc? The coordination geometry.
Mostly tetrahedral, but some look distorted.
Right. So tetrahedral is definitely correct, and distortion is most possible, especially because you probably will have a lot of crowding and other amino acids that are interacting here. All right. So you said, can the soft and hardness of protein domains be correlated associated with the solvent accessible surface area? And yes, indeed, it can. All right. And so depending on how accessible, you can have the effect of hydrolysis. And so that's what we will talk about in a subsequent lecture. So that's a very good question. Okay. So you can imagine certain proteins, in order to interact with a metal center, may have to induce a sort of closed environment to be able to do so. All right, so good observation, tetrahedral geometry. Another important observation is that some of these sulfurs that are coming from the cysteines are bridging sulfurs. And what does that mean, a bridge? Well, for instance, this one right here is serving as a bridge between 2 different zincs. And some of the sulfurs from the cysteines are not serving as any bridge at all, so they're non-bridging. All right, so there are a number of different features here that helps us to understand how this pretty simple protein can really play a really important role in terms of stabilizing zinc and serving as a storage of the metal. All right, let's move on. Let's talk about metal interaction with nucleic acids. And so again, this is a type of polymer, right? And so we're going to look at it from the perspective of the building blocks, the nucleotides, right? So the monomers. All right, so let's look at the nucleotide. Here we have a representation of one. And so what are the features of the nucleotide? Well, we have the phosphate group. We also have the ribose, the sugar ring, okay? And then we have the base, okay? So those 3 components here, all right? Now, where is that phosphate group located? So here we have to look at it from the perspective of the sugar. Well, that is connected to the 5' carbon of from the actual sugar unit, okay? And then the connection of the base, well, that's occurring at the 1' carbon. All right, so let's look at this then from the perspective of these the building blocks with the different bases. We have adenine, you have cytosine, you have guanine, you have thymine. These are typical nucleotides that participate in the formation of DNA. And then you also have the additional uracil, which is typically what you will find in an RNA nucleic acid. Okay, so here we're just looking at the distinctions in terms of the actual bases. And that becomes important because here then you start to think about, well, what's capable of metal binding? And that's going to be a very important question. Well, let's look at the composition of a DNA strand, right? Well, how do we go from the nucleotides to then this polymer of nucleotides? Well, what's going to be very important is this chemistry here, the formation of a phosphodiester bond. Okay? So when we're looking at a DNA strand, we're going to read it from the 5' to the 3' end. What do I mean by the 5' end? Well, we're looking at the first nucleotide, and from this perspective, right here with this phosphate, the 5' end, and then we're going all the way to the next nucleotide, and what you will see then is over here the free position of the last nucleotide at the 3' end. Okay, well, why am I emphasizing that? Okay, well, that's the typical way of reading it, but also very importantly is the union between one nucleotide and the other. Okay, that union there is going to be really critical. So the phosphate group at the 5' end, and what you're going to see is that the formation of a phosphodiester bond. Okay, so I'm going to clean this up just a little bit to emphasize this, where you have the OH group from the 3' end of a nucleotide, right? That electron density being drawn to the phosphorus, and so then this will become protonated, and this will be a good leaving group. Okay, and so you get the formation of your bond here. That's going to be the link between the nucleotides. And so another really important feature that I'm going to emphasize here is that you have points, and you have these arrows here that are emphasizing points of potential hydrogen bond interactions between nucleotide bases between one another. And so these bases engage in hydrogen bonding, giving you characteristic base pairing. So you guys have heard of this, where you have adenine and thymine interacting, guanine and cytosine interacting. Okay, these are pretty common. Let's focus on that for a moment. Right, so here is an example of the hydrogen bonding capabilities, where you have the AT interaction leading to the formation of two really important stabilizing hydrogen bonds between the two, and how that leads to particular structures that you would see for DNA. In a similar fashion, you have the CG base pairing, which leads to the formation of these three important base pairs, okay, these three important hydrogen bonds, okay, that help to stabilize the structure. And so this gives us an idea of how we start to build up the dimensions of and the structure of this particular molecule. Another thing here that's highlighted, is the highlighted in green, is where you can have a potential metal bind. But I'll show you in a moment how this goes beyond just binding to the nitrogen example here of the base. All right, so just to give us a representation of a type of DNA structure, the B DNA structure. And so here we have like that classical depiction, the Watson-Crick depiction of the two strands interacting. So this is the sort of one-dimensional representation here. We have the 5' to the 3' end of one strand interacting with the 3' end and 5' end of the other. So that the base, the hydrogen bond pairing between the nucleotides of the corresponding strands. And then here you have this idea of the layering, the base pairing on top of each other to give you these structures. Okay, just to give us a perspective of what we should really be thinking about as a representation of a DNA molecule or of a nucleic acid structure. All right, so now looking more closely, so going back to sort of the simplified perspective of the sequence of nucleotides. And so what I'm highlighting here are points of contacts that can interact with metals, that can form bonds with metals. And so what you commonly see are the nitrogen and oxygen atoms of the bases that are capable, so these are all the bases, that are capable of binding to metal centers. So there are plenty of examples of that. You also have the oxygens of the phosphate group that are capable of forming a bond to a metal. And you also have the oxygens of the phosphodiester groups that are also capable of forming a bonding interaction. Now you can imagine a bonding interaction with a nucleic acid can result in a significant structural change, right? So that's something that's really critical, and actually some people try to exploit that when they're trying to develop something that can harm a cancer cell by targeting DNA as a primary target. All right. But here, what I'm going to show you is possible interactions with a nucleic acid, so metal binding to DNA in a very general fashion. So let's imagine here we're looking at two strands, right? And a typical interaction that can occur is the formation of an intra-strand crosslink. That means that you have a metal, this metal is depicted here, that forms a bridge between two guanine um, bases of the nucleotides. So you get that when that forms, it essentially creates a cross-link, and that's going to disrupt the structure of the molecule. But you also can have what are known as inter-strand links, where you have the formation of a bridge facilitated by metal binding to two guanines, and these two are coming from two different strands. And so that's why it's inter-strand cross-link. Okay, another type of interaction is that you have a metal coordinated to the the base of the nucleotide. So here the representation is the guanine, but that's also then facilitating an interaction with another biomolecule. For instance, a protein, causing a cross-link between a nucleic acid and a protein. Another level of interaction is imagine a metal compound. Imagine a drug that can insert itself between the aromatic layers, right? And this is a form of an interaction that's called an intercalation, where the structure of the drug is such that it can nicely layer into, and typically would be something that can induce sort of a planar structure that can nicely interact there and then cause a structural change. So this is something that is a possibility. All right, so I'm going to stop there, okay? And we're at the end of our lecture. So I'm going to assign you guys a first assignment. I will send you the instructions of what the assignment is and how specifically I want you guys to label your files. So have a great weekend, and I will see you guys next week. Take care.
Thank you,
Thank you.
Professor.
You
You
too.
too.
Thank you, you too.